Thank you. It's really wonderful to be here. It's the first talk I've given in person since February 2020, so I feel like I'm out of practice, but it's wonderful to be here and see people in person. So today I am actually speaking about a report that I led for the Department of Energy, the Basic Energy Sciences Advisory Committee. I'm the vice chair, and Mark Kastner, who many of you may know, is the chair. And so we were charged with by the Department of Energy to look into US competition in the context of basic energy sciences research. And this report has now been approved. It's posted online. Here's a very long link, but if you just do a search for BSAC reports, you can find it for 2021. So basically, we are asked to look at this question about, can we compete, can the US compete in basic energy sciences? And I'll give you the answer next, the Cliff Notes version, which is yes, we can, but action is needed to be able to maintain and to bolster the position of the United States in basic energy sciences, and in particular physical sciences in this arena. As I'll articulate, scientific discovery, or I'm asserting here, is really, I think, the cornerstone of American prosperity. Basic energy sciences, and basic science in particular, is important to drive innovations. It takes time to do so, but it's critical. And our task really was to benchmark the US research efforts against global competitors in these specific areas. And in brief, our findings show, and I'll show you the data, that other nations are rapidly catching up with the United States in these arenas and actually overtaking us in some areas. And I'll talk about how we measured this and how we concluded this. At the same time, we did identify strategies that we think will have a major impact or have a potential for impact on increasing and enhancing our competitiveness. And I'll talk to you more about the team later, but what I want to say is we assembled a subcommittee of a team of subject area experts in these fields, and actually ZX Chen was one of the co-leads of this, along with other distinguished scientists, and people who also were experienced administrators who had international experience. So one example being Helmut Dosch, who some of you may know. He's the head of DAISY. So this is the summary of our charge. Basically, what we are asked to do is to identify key areas of mission-relevant science, and in particular to identify scientific areas and facilities that are critical to US competitiveness and those that are in particular most threatened. We also were asked to advise on modifications to existing trade-offs and also new ways to leverage resources, which of course are always scarce. And then finally, to identify incentives that will retain and attract scientific talent. And in my mind, this issue of scientific talent is probably one of the most important aspects of this report that we should consider. And I'll be talking about that in more detail shortly. One thing I want to point out, I want to put this in context in particular because there are early career investigators in the audience, is that the Department of Energy Basic Energy Sciences is basically the largest funder of physical sciences in the space that we're talking about in the United States. And so that the impact of the work in this area has importance for basic science as a whole in the physical sciences, as well as on energy leadership. This is just to show you an example. This is taken actually from a slide from the last BSAC meeting presented by the director of BES, Dr. Linda Horton. And it shows the various numbers for the budget for the basic energy sciences. And in particular, I want to point out that the research budget for fundamental research is $871 million. And the scientific user operating budget is $947 million. So it gives you an idea of the order of magnitude of funding that's available in this arena of science. Now what I'd like to do is to, before talking about the results of our report, to actually talk about the context of how science was funded and how we ended up with the federal funding system that we have today. So if you ask yourself how science was funded earlier, in particular prior to World War II, the answer largely was through philanthropy and also through industry. So there wasn't significant federal funding prior to World War II in the United States. And I've got two examples here that are kind of interesting historical ones. On the philanthropic side, Arthur Loomis, shown here, funded a private research facility called Tuxedo Park. It's in Tuxedo Park, New York. And he was instrumental in the development of radar. And he basically funded this in the 1930s. He was a financier, so a venture capitalist, but was very interested in science. He also then, and when he had developed, besides developing radar at his laboratory, shown here, he also helped to establish a top secret defense laboratory at MIT, and in fact also lobbied with E.O. Lawrence, lobbied FDR to do research in nuclear fusion, which led to the atomic bomb. So this had a huge impact, this philanthropic investment, on the face of how the World War II proceeded. On the other side, there was industrial investment in science. It, of course, had more of an applied bent, but if we take one example, and this is from chemistry, DuPont Research actually started out by funding a lot of research in polymers. So I'm showing here Wallace Carruthers, who actually was a Harvard faculty member in organic chemistry and was lured away by DuPont. He was the inventor of neoprene and nylon. And then, of course, DuPont has invented many other polymers, Teflon being an example. And so this actually led to the formation of DuPont Central Research Labs that combined fundamental research with some then idea of applied research in the future. They had other fundamental work that they supported in the 1960s, for example, and these are just some examples from chemistry. But the point here is that early on, the United States did not have a significant amount of federal funding that was provided for scientific research. So it was very different than the landscape we have today. What brought us to the point we are today was significantly affected by a report written by Vannevar Bush, who is the science advisor to Franklin Delano Roosevelt. This report was issued in 1945, and it was called the Endless Frontier Act. And for those of you that have been paying attention to the infrastructure bill that's being considered by the Biden administration, there actually is a plan or proposal to fund significant amount of research funding, and it's referred to as the Endless Frontier Act in reference to this report. And basically what Bush recognized is the central role of research, and he specifically called out things like the development of radar, the availability of penicillin, so things that stem from very fundamental research, how that had an important impact on society, and he thought that scientific progress was really essential to public welfare. And so I've just basically summarized some of the points that were made here. This is a picture of Vannevar Bush on the cover of Time magazine, so it's kind of old school. He was visionary, and one of the important outcomes of this report was the creation of the National Science Foundation. But more broadly, it led to the significant investment of the federal government in scientific research. So things that we know about today and that we all rely upon for our scientific prowess in the United States. I also just wanted to come back to this point. Why is basic research in the physical sciences important? And one is, I'm going to again reassert that fundamental research ultimately can lead to very important impacts on society, oftentimes unintended. So things that started out as curiosity-driven research can have big effects on the economy, on human health, national security, and the like. And historically, the US has been a leader in all areas of critical to BES research, but especially in the development of instrumentation, both at the laboratory scale and also at the large-scale facilities like those that you have here at SLAC. The other thing that we think is important, and you'll see this emerge in the report, is that a combination of competition and cooperation on a global scale is very important for the progress of science. Science is global in nature, and it's important to recognize that and see how that will drive things forward. And then there's also a very critical need to diversify the scientific workforce, but also to basically strengthen the scientific infrastructure. So these are important points that emerged from our report. Okay, so our key findings are listed here. And first of all, I think some things there, I guess not. It looked like there's an extra space there. But first of all, other nations, as you'll see, are overtaking us in the critical areas that we identified. And in the latter part of my talk, I'll talk about the methodology we use to identify those. Also, we found that support for small and mid-scale instrumentation is diminished. And there actually is something missing here, and that is that large-scale facilities, while still a traditional strength in the United States, they're still strong, but they're no longer unique, and the access isn't as wide as it was before. And then finally, and very importantly, is the competition for global talent is increasingly tough, and something that we really need to attend to, because we need people like those of you in the audience to make the future workforce that's going to drive innovation. So first, let's take a look at some of the data that shows that the United States is actually falling behind in various critical areas. And here's one example, which I'm showing you, and this is one part of the methodology we use, the worldwide fraction of papers in the top 20% of citations as a function of time. And so we did this, we are integrating them over this period between about 1990 and 2020. And what you can see is, by region, that there are substantial changes over this time period. So if you take the blue as an example, shown here, that's the United States, and you can see that in the last decade, the fraction of these papers that comes from the United States has diminished significantly. At the same time, if you look at the red curve, that corresponds to China. The fraction in this particular area, which is energy storage, so like battery technology, these have have basically, in one case, gone dramatically up. In the case of China, significantly down in the case of the United States. And if you look at the expenditures on research and development in China versus the US, what you can see is there's nearly flat funding for US science and overall in basic science. Whereas in China, it's gone up substantially, and particularly accelerating in 2010. So, this is a qualitative correlation, but it shows that there's this correlation between impact and the investment in science. So there's this downward trend. The increased investment by both the EU and China, and in some selected areas by other parts of Asia, have led to this change where the United States impact is no longer dominant. So I'm showing here for the specific case of energy storage, but in other areas that we identified, this is qualitatively reproduced. So this data is not as beautiful looking. It's taken from the appendices, so it's not smooth, but you can see again, the general trend is similar. In this area is quantum information science on the left. In the middle is quantum materials, which is the material synthesis emphasis. And then on the right-hand side is sustainable science, which is electrocatalysis and polymer upcycling. And in all cases, you can see, in particular, the red curve going up. And you can see that in many cases, or I guess in all these cases shown here, you have either flat or diminishing impact. Again, using these publication metrics as one example going down. So, if you think about some of these examples, if we take the case of the material synthesis, the quantum materials, there are various causes for it. And if you take one example of falling behind, at Bell Labs, the US was a real leader in the development and production of novel crystals and quantum materials. But then that effort was shut down. And so in the 80s and 90s, actually to get new materials or to get high quality materials, one had to go to other countries, and for example, Japan is a leader in that, and I think that is something that people are well aware of here at Stanford. So this is just one anecdotal example of the kind of changes that have led to these trends that we're observing, this in particular in the area of quantum materials. Okay, so if we come back to the other key findings, we can then look at facilities. And as I said, although we've been a leader in the United States in facilities development and use, they're not unique any longer. And so if we take a look at some of the selected data, and I'm only showing some of the data, these are for synchrotron facilities. If you look at the facilities available throughout the world, the purple and the gray correspond to United States facilities. There's a legend here that shows specifically what they are. And if you look at the brightness and photon energy, you can see that the US falls in this regime. You can see that China and the EU either have or are planning facilities that are either comparable or better in these areas. And then in addition, if you look at the capacity for doing experiments at synchrotrons throughout the world and compare where we were in 2000 versus in 2021, the thing that's notable is the fraction of capacity, beamline capacity in the US. It was 37% in 2000 of the worldwide capacity. It's now 26% in the US. Whereas at the same time in Asia and Australia, 29% capacity in 2000 compared to 40% in 2001. So it's an example, in this case, for synchrotrons, but again, it sort of reproduces itself for other major facilities. Yes?
What is capacity?
Capacity means like the ability to get beam time. So it can mean beam lines plus accessibility. So in order to do experiments at a synchrotron, you need to, as many of you know, you need to write a beam time proposal. So the availability of beam time to a user who's a non-expert user is more limited in the US. And actually part of this, which I guess is not shown on this slide, is also staff support. So that there's much greater staff support in Europe in particular, so that if someone's a non-expert user, and I'll take myself as an example, our group uses synchrotrons. We've done work at ALS and also at NSLS. There's much more support for that kind of work for non-expert users in Europe. Okay, thanks. Okay, then I want to focus also a little bit, I'm just kind of going through these different points on the fact that it's not only about large-scale facilities, but innovation at the laboratory scale is also important. So being able to build and invent new instrumentation at the laboratory scale is very important. I'm just using, again, 3 historical examples. One, for example, is the development of magnetic resonance imaging. Also, it's the same tool is used for chemical analysis, nuclear magnetic resonance spectroscopy. This was developed based on some very fundamental physics that was done by Pound, Purcell, and Torrey in the 1950s. And basically just out of curiosity to try to understand what was going on with nuclear spin. But it's now led to developments in medicine and also in analysis. Of course, we don't have to talk about the impact of the development of semiconductor technology and the transistor, which was developed by Bardeen, Shockley, and Bretan. That's another example of very fundamental research looking at the physics of semiconductors that was very important. And then the third example I have here is the development of lasers. Again, fundamental research that has revolutionized so many parts of our lives and of our world. So building smaller scale instrumentation and developing some of these ideas is also very important for driving science. And this is another area where there's been lower investment over the last few years and less of a commitment in the United States. And here are some current examples of people who are building instrumentation to try to do some work. These are just examples of laboratory scale experiments. For example, at University of Pennsylvania in the laboratory of Jessica Anna, they put together an important ultrafast laser spectroscopy system shown here to be able to understand better solar energy conversion. And this is Charlie Sykes at Tufts University with 2 of his former graduate students who's developed methods using atomic scale imaging using scanning tunneling microscopy, which is now a well-established technique, but it was invented in the early 1980s as a laboratory-based instrument. So driving innovation and investing in the development of mid and small-scale instrumentation is very important. So lastly, in terms of the findings, I just want to cover the importance of attracting and retaining talent for science. And again, many early career investigators here, graduate students, postdocs. This is an important aspect of, but it's going to be, driving innovation in the future. And what we find is that, as I think all of us would, well, at least I hope that you all agree that talent recruitment and retention is critical. One thing that was noted in particular by international participants on our subcommittee is that historically the United States really was considered a destination for science. So people, for example, in the EU came to the US either as graduate students or postdocs, and even if they went back to their home country, that was considered essential for their success. That's no longer the case. It is now, in fact, that many people are being recruited to stay or to go to Europe from other countries. And part of what's challenging is that other countries offer more sustainable research funding. I'll come back to this. But grants and support for research in many countries is more generous and more widely available than it is in the United States. And I'll touch upon, for example, European Research Council grants that are available at various career stages. In China, there's the 1,000 Talents program. Germany has Max Planck Institutes, and Switzerland has the ETH, the Swiss federal schools, for example. And then, as I already alluded to in answering the question about facilities, the wider access to advanced research facilities and more staff support is also another factor in retaining and recruiting talent in these areas, because it's a way of training new people and using these advanced facilities. I wanted to give a couple of examples. So I'm mixing in here things not just in my report, but other aspects of my own personal views that are related to the report. And that is really the need to support exciting research at early career stages. And I'm going to use two examples here of people who have Stanford connections, since I'm here at Stanford. They were both Roland Fellows. It's an independent fellowship at Harvard where they can start out an independent research group before being a faculty member, and to try to do high risk, high reward research. So with this support, these two individuals who, Dan Congreve is now a professor of electrical engineering here at Stanford. He just joined a little over a year ago, and he's a Moore Inventor Fellow. He was able to start developing new ideas using light up conversion to do 3D printing. He started a startup company when he was still at the Roland Foundation, and now is on the faculty here. That early stage support to do research that was very risky, I think is important as an example of a kind of program that can be helpful for attracting and retaining talent. Hao-Tian Wang is now a professor at Rice University. He's a Packard Fellow. He's working in electrochemical conversion, and he was a graduate student here with Yi Sui's group. He's another example of someone, again, who started this independent work and was able to get started, to be fully supported. And I think that these kinds of programs are examples of how we can retain and attract excellent talent, including, I'm sure, many of you that are here in the audience today. The other aspect, though, is moving onward after the very early stage that I just discussed, is that we need to boost support for scientists at all career stages. And if we start with the early career stage, other countries actually have larger and more generous programs than the United States. And just taking an example of DOE has early career research programs. Many other funding agencies do as well, but if we take the DOE as an example, there are typically 50 awards given per year for university researchers at the level of $750,000 per year, which is generous compared to most federal grants. There are 30 or so grants to National Laboratory to early career investigators. Typically, they're about $2.5 million over 5 years. So those are generous in the context of US funding. But if we contrast that, for example, with European Council starting grants, there are about 450 awards given, and at $1.8 million for a period of 5 years. And in addition, there's another €1 million opportunity if you have other ideas to add on to those basic grants. So there are a lot of opportunities to do research and over a more extended period of time for early career stage scientists. And if I take some examples, again, now this is drawing upon my own group of people who have chosen different pathways. I have 3 separate people, postdocs from my group recently took positions. And 2 of them are in the US, Fang Zhu and Nat Egan, and so they're basically having to compete against many other people for a smaller amount of money. Jesse van der Hoven, who just went to Utrecht University, has more secure funding for an extended period of time. So these kinds of early career stage individuals need the support to be kept in the system. Oops, sorry. At the mid-career level, there also is a need for boosting support. Part of the challenge is, even though there are these nice early career investigator awards that I mentioned available, there is not a pathway for automatic continuity. So if someone has an early career award, once that 5-year period is up, they compete on the same playing field with everyone else, except they may not have as much experience as someone who's been in the field longer. Furthermore, there is not continuity beyond 3 years for most federal grants, so there's virtually no opportunity for a mid-career scientist to have sustained support, especially for individual investigator grants. And if you just compare that, the ERC will give grants to individual investigators for about 2.5 million euros for a period of 5 years in this same career stage. So you can see that the competition for global talent is stiff, and it's something where the United States is not as generously investing as other countries. I want to emphasize the importance of international talent recruitment. This is something historically the United States has depended upon, and I won't go, I don't want to make this a history lesson, but if you look back historically in the United States, many international researchers have come in and had substantial impact on work in particular in the physical sciences. That's still the case today, and so these are just 3 examples derived from stories that are contained in our report of individuals who came to the United States either as postdocs or graduate students and stayed and are making important contributions. And included in this is one of my colleagues and collaborators, Joanna Eisenberg, at Harvard, who came to the United States as a postdoc and is now a very distinguished scientist at Harvard University. Elke Ehrenholz is another example of someone who came to the US as a postdoc, and she is in the national lab system. She just recently moved to Oak Ridge. And then Tao Sun came as a graduate student, and he has stayed on as a researcher in the high-tech industry. And so these are 3 examples that illustrate the point that I want to make, that attracting and retaining international talent, I think, is critical to the success in the United States. Oops. So if we come back now to the last point, not last point, but the point about facilities, which is that we have had historic leadership, in particular in the DOE complex, in advanced facilities. And I'm just showing 2 examples here. The NSLS-2, which is the synchrotron, one of the newer synchrotron sources at Brookhaven National Labs. And then this will all look familiar to many of you, especially Norbert, but we have the LCLS up at SLAC, the X-ray free electron laser that was established in 2010. These are examples of important facilities. On one hand, synchrotrons are more established and mature technology. And one point that we make in the report is that the synchrotrons have enabled a lot of excellent research, even though the people who use them are not necessarily experts. And so we give examples of 7 Nobel Prizes awarded over a 25-year period using X-ray synchrotron sources for all kinds of applications. One recent example is in the CRISPR-Cas9 research that was done by Jennifer Doudna. She used synchrotron resources in order to get information about structures. There are many other examples, again, articulated in the report. At the other end of the spectrum is looking at developing facilities that have unique capabilities, like the LCLS and now the LCLS-2, which has very short time duration X-ray pulses with high brightness that can probe time-dependent measurements, like, for example, photosynthesis processes. So the facilities play very important roles in this, but they're not unique, as I showed previously. They're being developed in other countries. there is more access to facilities that are established like synchrotrons. And so that is one of the challenges that we face. Now, why are these facilities important? I talk about the Nobel Prizes, but of course there are many other uses, and I just have a few examples here in the DOE context. Critical research is enabled at large-scale facilities through other kinds of team research like energy frontier research centers. Here are 3 examples that are described in an article written by an early career investigator for EFRC Frontiers Research newsletter. But basically, they've done, these 3 examples show research using synchrotrons ranging from understanding lithium-ion batteries all the way to understanding the breakdown of biomass, and by looking at the walls of cellulose crystals in plant, the cellulose crystals in plant walls. And so you can see there's a wide range of different kinds of problems that can be addressed by facilities like the synchrotron facilities. In our work, I'm going to sneak some of my own science in here, I can't resist. We've been able to use synchrotron sources to get information about the detailed structure of nanoparticles that are very dilute alloy particles, and so it's challenging to find out the distribution and arrangement of a second very small fraction metal in these materials. And it combines advanced computation with X-ray scattering, so machine learning. And this was actually a collaboration with groups here at SunCat at Stanford, including Matteo Caniello and Simon Baer. Likewise, smaller scale facilities, so I want to come back to this point about smaller scale instrumentation is important. These are a couple of examples from the DOE complex. So for example, at Brookhaven, in collaboration with several different universities, there was a so-called quantum press developed, which is designed to make multi-layer materials in a continuous fashion, so it's designed to be very user-friendly in order to drive forward research in quantum information science. At Columbia and the EFRC, they also are working on looking at electronic magnetic transport in materials at very short time resolution and at a small spatial scale as well. So these are just some examples of developments of instrumentation that are important. And then of course computational facilities are something that we also looked at. Computational horsepower and large scale facilities cut across all the different areas of research that we looked at. And I've just given a few examples here, ranging all the way from machine learning to understand protein self-assembly to some work with machine learning for catalysis development. And then I'm showing here the development of a quantum simulator at Harvard in the lab of Misha Lukin. So basically what we want to be able to do is to be able to balance the advances of world-leading research facilities with a need for improved access and technical support to those facilities, but also at the same time to be able to enhance the development of small-scale instrumentation. And I couldn't resist putting this in, since Steve was here. But what I want to point out is that we also found that it's important to think about how to accelerate the transfer of basic science to applications. And I'm using this because Bell Labs, of course, was a very important driver of this, and I'm showing a picture of Steve and Arthur Ashkin in 1986, and of course the beautiful work that was done with atom trapping and then optical tweezers, which was absolutely transformational in physics. But there are many examples at Bell Labs. There's, again, a great book about this. The lack of this kind of ability to take fundamental research and translate it then later into applied research is another issue that was identified in the report, the need for this kind of translation across fundamental research. And so there's actually a BS workshop that looked at this called Transformative Manufacturing. But the point is that there is a goal to enhance both fundamental discoveries and technological advances by better integration across basic research to applied research. So that was another challenge that we identified. So I did want to just briefly talk about the the methodology we use, and I'll try to be brief about this. I can answer questions if there are any. I've asserted various conclusions, and I wanted to tell you how we went about doing this. So first of all, we had to identify what we thought were the critical areas of research in the BES space. And we use these so-called basic research needs reports to be able to do this. And the Department of Energy uses workshops to talk about the most important science and identify critical questions in specific areas. This has been going on now for quite some time, and so there's a large library of reports available online. And so what we did is we examined those, and we used those to down select by first getting expert rankings both from people who are leaders of those report studies, and also because we had subject area experts in our subcommittee. Based on that, we then identified 5 particular areas, which I'll tell you what those are in a moment. Area 5 has to do with instrumentation, which is cross-cutting. And then we also further narrowed things down to look at in order to be able to decide which ones were really warranting a deep dive, because there are many, many of these reports. I'm going to say there are at least 40 of them that we examined. But we boiled those down to 5 different areas. We then used a combination of publication metrics, where we engaged library scientists to be able to get detailed information, and also analysis of conferences. So we looked at where speakers for plenary lectures and invited lectures were for key conferences in the different areas, so that our subcommittee members identified those. And then we used that to do the quantitative ranking, like the example data that I showed you earlier in the talk. There's a more complete set of data in the report itself. And then we also examined awards in the different areas of interest here. And finally, we had webinars to get input from the scientific community at large through the American Chemical Society, American Physical Society, Materials Research Society, and Electrochemical Society. So this is how we identified the areas that we were interested in and their ranking. And basically, I want to point out that although we looked at only specific areas, we think that the general conclusions, because they were so similar in every single area we looked at, would apply across the physical sciences as a whole, even though we didn't look at everything explicitly. And the specific areas that we looked at are shown here. They were grouped together. So for example, quantum information science includes quantum computation, quantum communication, simulation, and sensing. We looked at science for energy applications, which includes energy storage, membranes, which are very important in, for example, batteries and electrochemical cells, separation, and then interfaces. And so you can read on down the list. And as I said, at the 5th area was advanced research facilities and instrumentation, which cuts across all these different areas. And so when we analyze publications, for example, we would look at what facilities were used in order to produce the data in those very high impact papers. And then in addition, we had to look at qualitative data. Besides the data just examining publication metrics, we also had many consultations. So we had a second team of our subcommittee that basically conducted consultations with a wide range of people in the scientific community. And you can see who is consulted. It included National Lab Leadership, National Science Foundation, private foundations, universities, international leaders, early career scientists, and then also we consulted people in industry across the globe. And so what we found is from this input is that the qualitative types of things I described, like the issues about talent recruitment and the importance of sustained and more continuous funding for people at different career stages. Oops. You can tell I'm out of practice using a slide changer. So lastly, I'm just going to close with, we also illustrated the points that I made here with various stories in the report so that it could be more accessible to a wide range of audience. And this is, doggone it, sorry. just doesn't want to stop on this slide. So there are a number of different stories. I'm not going to read them, but they're contained in the report. But they illustrate the points that we made and the points that we made in the report were supported by the quantitative data and the qualitative consultations that I already referred to. So if you're interested, you can read each of these stories. I just touched upon two of them. One is that we noted the importance of long-range strategic planning, in particular for building facilities, so that kind of longer-range planning is important in the future. It is what led to, for example, some of the success stories. For example, the planning that led to the LCLS building. But in the future, we also have to think about what is it that we actually need to support the science in the United States most effectively. So this is one example of the story. And just a second example is about quantum communications and some work that was done at Argonne National Labs. But quantum communication is very important for national security. It's also, though, a very interesting phenomena. And this is a story that highlights the work by Alan Debos, who's at Argonne Labs. So you can learn more about some of these things in the report itself by reading some of these stories. So again, the final takeaways are here. I've already gone through them in detail, so I won't read them again, but I hope that I've at least given you the flavor for what our committee did, and hope that I've energized you to think about some of these issues. And one of our goals is to be able to use this report as a vehicle to have discussions with people in government in order that they can understand the importance of basic science and funding this important work that is in the physical sciences. And lastly, I just want to acknowledge the team, last but definitely not least. And as I said, there was a core group that met rather frequently, and I want to in particular thank ZX for the leadership role that he played. He brought up many important points and helped focus us. In addition to ZX, Matt Terrell from University of Chicago was the vice chair. Eric Isaacs, the president of the Carnegie Institute, also was a team lead along with ZX. And then important leadership in basic energy sciences. Jeff Miller, who actually works at Harvard with me, is a condensed matter physicist. He played a very important role in logistics and data analysis, and Al Hammond is a well-known science writer who actually wrote the report. And you can see that they're a group of very distinguished scientists in many areas of science who, both internationally and within the United States, who were part of this subcommittee. And then last but not least, there was also support for logistics and the technical aspects shown here. But it was really a great team. It took a lot of energy and work during a very challenging time period, because this was during COVID times, to come to these conclusions. So I want to thank and acknowledge all of them. And I'll just go back to our main conclusions and stop and answer any questions. But thank you.
One is that, the data you showed from the European community versus the US is pretty startling. I didn't realize there was such a big difference. But in fact, it hides an even stronger unbalance. And that is the fact that there's also stuff you don't pay if you are in Europe.
I'm sorry, there's what?
You don't pay technicians, you don't pay, so it's actually that money goes even further.
Right,
because
right.
At least the universities, you pay every dime of everything, right? So that's the first thing. The second is, I'm wondering whether there is an almost irrecoverable kind of loss that has to do with things like Bell Labs. So the industry doesn't work the way it used to work. And
right.
The government can throw more money at research, but it's hard, it can't affect how industry does stuff. And it seems like we've sort of changed in a way that doesn't encourage basic research anymore in the industrial setting. Industry makes phones, and they just buy transistors from, Apple doesn't think of developing new transistors. That's just not their business.
So I can comment on that. This is not part of the reports. I'm going to give you now my personal opinion. I do agree that research isn't the same as it used to be. So if you take many of the great research labs, Bell Labs, GE, DuPont is another example in the chemistry arena, that's gone by the boards. And it is because of pressure on the bottom line, and honestly because of international competition, I would say as well. But if you're a high-tech business, you actually can expend some amount of money on innovation. And particularly, I would say in the instrumentation arena, it's something I'm personally familiar with because of some work that I do. So that I think there's still an opportunity, but it's not at the scale of a place like Bell Labs. And I think some of that could be, I mean, in the case of Bell Labs, it was the breakup of the monopoly of AT&T. So there was a specific business reason, but I also think it's the focus on the bottom line that is driving it. That's not going to change. So if you were to ask me, and what came out of the report, how we might think about that, perhaps a better integration between fundamental science and applications is one way to do that, which you can have your thoughts on it. Stanford does a great job of this, of course. To have basic research that then can lead to technology and have that technology transfer occur rapidly. What it won't do is it will not lead to, for example, growth of really great crystals that you don't know what they're really going to be used for. That you're not going to recover unless we have some facilities like that that are funded by the federal government, in my opinion.
Of course, the unfortunate reality is that many of those strategies involve spending more money.
Yes.
And it's a hard situation when there are so many other priorities that the country has. I mean, one of the things that is perhaps informative is to think about in the same period where physics funding has suffered, funding for the life sciences has perhaps flourished, you could argue.
Yes.
And there might be lessons to learn from that. Why did the NIH do so well in this period when other federal funding agencies did less well, certainly in comparison? Part of that was the driver of big national health priorities like cancer was one. And of course, there's hope, I think, that some elements of sustainability and energy associated with that will also be a driver of physics-related research. But do you think there's other lessons to be learned from the life sciences side?
Yes, I think we have to be a little careful. So again, I alluded to the Endless Frontier Act. I don't know how many people have been following that. There actually is the proposal on the table to double funding for NSF. The catch is, which is not unrelated to the previous question, is that a lot of that additional funding is targeted to go into an applied or engineering side of work to create a second branch of NSF. Personally, I'm not a fan of that, I will say. As a private citizen, I have to say, not as the president of a philanthropic foundation. So I think that basically the idea for this did stem from the fact that NIH did double their budget, just as you said, and it's because people's imagination were captured. So I think in order to be successful at increasing the budget, we need to capitalize on public understanding and belief in science, and I think the sustainability and climate change is a perfect example. It's a critical problem that we're facing right now, and it's one that we could imagine, in particular in the basic energy sciences space, building upon. I think the key is to, from my point of view, and again this is my personal opinion, to make sure that basic science is recognized as being important and not just to go the applied route. But at the same time, maybe the applied route would address the issue about, a crystal growing facility, for example. I don't know. That's an interesting thought because it's building up infrastructure as opposed to just funding individuals. But you need to fund the people too.
Other questions?
Yes, maybe I have one. So, ES in particular has been successful in growing its budget inside the DOE actually quite a bit, right?
Yes.
If you look back 20 years or so, it's more than doubled. The strategy for doubling this was building facilities.
Yes.
Now, if I read the strategies correctly, and I, by Linda Horton, I would conclude from this that I take this money that I have, and I don't necessarily build new facilities, I do other things. Is that the message in this report?
No, it's not that straightforward. I think what I would say is there needs to be a long-term strategy in facilities. That's in the report. So it is not saying don't build more facilities. Don't worry, Norbert. That's not in there. And that's not our recommendation. But I think that the recommendation is don't only build facilities. You need people as well.
But then how do you grow the budget?
Well, I think what we just said, you have to capture the imagination, first of all, of Congress, in my opinion, but also that means you have to capture the imagination of the broader public to believe that there are important problems facing our society that basic science can have an impact on, if not immediately, then at least in the longer term. But it's a harder sell, no question about it. If you have a facility that is very visible, that is something that someone in Congress can understand what that is, as opposed to a distributed program that doesn't have necessarily the obvious impact. And it comes back to the proposal for the NSF. Part of what is being proposed is building sort of hubs or facilities in places where there aren't those kinds of things, in places where there's not a strong science presence, and building up infrastructure to do technology transfer, if you will.
Yes, Jake.
So, did you look at, is there a rate of funding, so you can look at the probability of getting funded if you apply for a grant, and also the amount of funding that's achieved. Do you find that there was a probability below which things become pathological? And secondly, did you find that there's an amount that is a good choice or an amount that's so low that it's not useful? And then I guess as a counterpart, you look at not quite another limit, but close to it, the Max Planck Institutes, the directorships. Do you look at how positive and high the impact was there for the amount invested?
Yeah, so we did not look at those numbers because I think it'd be a very hard thing to get at. Your question about, let's start with is there a probability of getting funded at which it becomes pathological, to use your term. I'll give you my opinion based on just anecdotal evidence, and I think this particularly shows up for mid-career scientists at many institutions. I think the answer is at some point people just stop applying. If they write 10 grants and don't get anything funded, they just stop. And I've seen it happen. And people who are excellent scientists who were tenured, but they just can't get funding for whatever reason. So I think that there are some examples of that. You could argue why it is that that's the case. And I'm not going to go there. But yes, I think there is a number, but we didn't look at that in the report. I also think that yes, there's a number below which it doesn't make sense to have a grant, because if you can't even support one graduate student, or maybe only one graduate student if you're lucky, that's not a research program. You have to have a critical mass. And I do think that that is one of the challenges for individual investigator grants across many funding agencies. It varies quite a lot, but if you can't have an actual meaningful grant, then that is becoming problematic in terms of how science pushes forward. In that sense, some of the center grants, I will say, I think that, and I think also national lab programs can give you a critical mass that doesn't depend just on one group or just a couple of students. But you can, again, argue about that. But I think you do need enough funding that you can have in whatever the critical mass is in your particular field to be able to do meaningful work. But we did not look at that.
You made a very clear case for the challenge of attracting and retaining global talent. We have to
Yes.
think internationally. What about, related to that, is also international collaboration.
Yes.
And that is not necessarily viewed with enthusiasm these days in Washington.
Yeah, so we actually tried to steer clear of politics in this report, as you can imagine. Especially, we started this before November of last year, let me put it that way. So we were very careful to not politicize the report. But and again, now I'm giving you my opinion as a personal citizen, I think that international collaboration is absolutely critical. And that's one of the things that attracted me. My current position at the Kavli Foundation, we do have an international footprint. I think international talent is essential to the United States, but I think this exchange of talent and the collaboration, first of all, is inevitable because the world is very interactive, and I think, as scientists, we know that. Unfortunately, the political landscape is not supportive of that right now. So I think the best we can do is to try to maintain what we can as scientists and as organizations and institutions like Stanford and Harvard and foundations to make sure that we don't lose that connection, that we don't fall into that trap. But it's a difficult time. It's a very challenging time, but I think it's important that we keep reiterating the importance of the international component of what we do.
I know you're talking about how sort of important high risk, high reward funding can be.
Yes.
Obviously that means sometimes things fail.
Yes,
And so
absolutely.
Do you have any ideas for how to continue to capture people's excitement even when there is failures?
Well, you have to not have everything fail. So you have to have some successes. But if I would, and this is, again, I think a luxury of philanthropy, private funding, is you can take that chance. You could also say on the industrial side, that's what venture capitalists do. They don't expect everything to succeed. You just need 1 out of 10 things to be successful. So the advantage of doing something a little riskier is that there's a much bigger potential upside and you can transform things, whereas the way federal funding is now, and this is again my own opinion across the board, not specifically for a particular agency, is the process is very risk averse by its design. And so we're always looking for reasons not to fund something. And of course, I agree, we should be critical. But we have to try some ideas or allow some ideas to develop that are out there. So there needs to be some room to fail and then to make a course correction. You don't want to, continue on a failing pathway, but you can course correct. So you just have to make sure that that's articulated. And people understand it and, make a big deal of how great it is if you're not really successful entrepreneur unless you've had a couple of failures. You hear that all the time. I mean, in Silicon Valley, you hear it all the time. That's kind of glorified and glamorized. So in science, maybe it shouldn't be quite in the same vein, but I think we have to have the ability to have some failures.
One more question over there.
My question comes down from the standpoint of an early career researcher who's looking to fund a group for the first time, and looking at like the 50 University Dewey early career grants, which are generous in the scheme of things, but also only supported to graduate students, but as of before. What do you think the realistic probability of a more widespread upgrade or rethinking of the way that the federal system of grants exists within this country to support more of this long-term vision establishment and research labs for research?
So you're asking if it's likely that we can be successful at convincing, let's say, the government to do this. I don't know. I mean, I think that if we don't try, it won't happen, is sort of my viewpoint. And I think it's important for senior leaders to try to make that point so that there can be opportunity for future generations. But I think it'll be difficult to make the argument. And it's not only just supporting early career investigators. It's, I would say even more critically, it's that mid-career point that's very challenging, because there are people who aren't yet really established and senior that don't have the benefit of the doubt and don't know how to play the game as well, but they also don't have their early career awards. So I think we need to focus on both of those. But we have to try. It's challenging because, as someone said just a few minutes ago, there are many other priorities that our government has for funding, and we just need to make sure that science stays in the forefront, I think.
So I had a more specific version of Peter's question. If we take a typical physics publication that's international collaboration, what were your metrics for deciding whether, for example, this publication goes on the blue curve versus the red curve?
Yeah, so we did look that. We looked at who the corresponding author was, but we did look for collaborations. And the other thing we looked at, which we didn't really correct for it, but it is something that shows up, is what I'll call home field advantage. And this really showed up in conferences. But if, let's say you're organizing a conference in the US, or if you publish a paper in the US, then the citations might be slightly more heavy in the US arena as opposed to some other part of the world. So, with publications, there was less of that than with conferences, where there was probably travel restrictions and maybe language restrictions. So we did look at collaborations, but we just took the lead author and what the lead institution was to develop those metrics.
I just have one comment regarding to Giorgio's earlier point. I think this study really looked at federal funding, but the private sector is also something interesting to look at. One thing we learned during the interview is how the U.S. companies fund research. For example, in the area of quantum information science, you find the American companies are funding European research. Microsoft, Google, they are quantum information focused actually in Europe. And that has to do with how the intellectual property right. The European universities are more willing to negotiate, while the top US universities were not willing to negotiate. So it's a complicated picture, but because the money goes there, it has an impact on the ecosystem overall. Other questions?
Okay, well, thank you.
Okay, let's thank speaker again.
And even though this is the first time I've given a talk in a mask, it's great to be back in person.